All right, this lesson is analyzing units, level 1. Our learning goal is, given a framework for a calculation, analyze the units correctly to find the units for the answer, showing your work. Now, values in science include units. They come from measurements, and we need to handle the units correctly in calculations. In math, you learn that if the same factor appears in the numerator and denominator of an expression, it cancels out. For example, we use this in simplifying fractions. We have 12 over 15. Let's see if I can do this. So we can factor it into 4 times 3 divided by 5 times 3. And in turn, that becomes 4 over 5 times 3, making it into 2 separate fractions. But of course, 3 over 3 is just 1, and so we can finish up by replacing the 3 over 3 with 1. So we have 4 over 5 times 1, and our answer is 4 over 5. So that's math. No units in math. In science, we have units. Any value appears in both the numerator and the denominator. We can use the commutative property to show that we have a factor of that value over itself, and anything over itself is equal to 1. So we just take it out. We call it canceling. Since anything divided by itself is 1, except for 0, we're just multiplying by 1, which doesn't change the value. This also works in symbolic expressions. Suppose we want to simplify ab squared c divided by ac squared. So we can factor our ab squared c and we're going to factor it into a times b squared times c over a times c, where I broke up the c squared in the denominator, and it will become clear why if it isn't already. So that's equal to, that's equal to a times b squared, a over a times b squared over c times c over c. But that, of course, is just equal to 1 times b squared over c times 1, or b squared over c. So we were able to remove one factor of c and a from both numerator and denominator. Okay, we can do the same thing with units. Units operate very much like a, b, and c in symbolic equations. Anytime the same unit appears in both the numerator and the denominator, we can cancel it out. For example, we might want to multiply 15 grams times 1 centimeter cubed over 2.7 grams. A number by itself acts as a numerator with that quantity over 1, so we could write it like this, and you're welcome to write your expressions with something over 1 to make clear that it's in a numerator if you want to. Now you can see we have grams in both, that is g, in both the numerator and the denominator, so we can cancel out grams, and we just line them out, draw a line through them. The only unit remaining is centimeters cubed, so that will be the unit of our answer. We can grab a calculator at this point, not sooner, to evaluate the numeric part of the expression, which is 15 divided by 2.7, and get 15 grams times 1 centimeter cubed divided by 2 grams is equal to 5.6 centimeters cubed, where the grams disappeared, leaving only centimeters cubed for the remaining unit. Including units is not only correct, it can also help you catch errors. Suppose you had made the mistake of multiplying by the fraction the wrong way up, like this. You would analyze the units and end up with grams squared over centimeters cubed. If you know from the context of the question that the answer should have units of volume, which is centimeters cubed, you would recognize that you had set the calculation up wrong, and you could go back and find your mistake. Sometimes we do get combination units. To determine the area of a rectangle, for example, we multiply length times width. Suppose our rectangle is 4 centimeters by 8 centimeters. So the area of our rectangle is 4 centimeters times 8 centimeters. What do we do when we have centimeters times centimeters? These are both basically numerators, right? Well, that's 2 factors of centimeters. That's centimeters squared. 3 times 3 is 3 squared. 2 times 2 is 2 squared. Centimeters times centimeters is centimeters squared. So A is equal to 32 centimeters squared. We can check. Are centimeters squared the appropriate unit for area? Yes, they are. Notice we get the same unit when we calculate the area of a circle. Let's find the area of a circle having a radius of 3 centimeters. Our formula for the area of a circle is A equals pi r squared. We substitute in 3 centimeters for r. A equals pi times 3 centimeters squared. Squaring 3 centimeters means we multiply together the square of 3 and the square of centimeters. So we have area equals pi times 3 times 3 times centimeters equals 28.4 centimeters squared, 2 factors of centimeters. Anytime we correctly calculate an area from measurements in centimeters, we will get correct area units of centimeters squared. In fact, anytime we set up a calculation correctly and analyze the units correctly, we will get the right units for the answer. It's important to always draw a horizontal, not slanted line between the numerator and denominator of a fraction. This helps you and anyone looking at your work know what is a numerator and what is a denominator.